Right, Dr. Chen, take away.
Okay. Thank you so much for the introduction. I think I have about 40 minutes, right? So, yeah, we basically summarize, what we have done in the last year, relevant to the federal learning and to this talk regarding the scalable, heterogeneity-aware and trustworthy federated learning. And also thank you so much for inviting me. Okay, sure. Yeah, thank you. So one reasonable advance, for this, for the machine learning, the federal learning. That's why we have this workshop, right? So basic idea is very simple. People have a lot of mobile devices or edge devices. That's by the way, I'm also the director of one AI institute working on edge computing. This is very relevant to my research. So if we're having those mobile devices and each device will face different set of the data, we try to train the model to deploy to these different devices by taking into account all the data we actually collect by using these mobile devices. And also we need to worry about the privacy because we don't want to share the sensitive information across the different devices. So that's why people came up with the federated learning, which is a little bit different from the distributed learning to do those stuff. So we don't really share all the data. And people have been using this federated learning for the different applications. One example is Google, and they actually use use in their transaction on the search, and also for the NLP, so such and such, and also some bank. There's one bank in China. It's the Wei Bank. We belong to the Tencent, I believe. They actually use a similar application, for this federal learning-based services. So if you look at the challenges of learning, it's basically besides the privacy, it's actually also relevant to the communication efficiency. Because we need to try and transfer not the raw data, but transfer the model information back and forth between the device and also the server. If you consider, the total communication cost, that will be the product between the communication round, how many rounds are going to transfer, and for each round, how many parameters are we going to transfer, and how many bits or the core words length we need to represent the different parameters. That will be the huge number. One example is the VGG16 on the internet night. We're trying to convert the whole model with 9,000 iterations. And we need to transfer 138 million parameters back and forth. And then for each parameter, we have a 32-bit because this would be the gradients we need to transfer. We need a hyperstation. If we add all of them things together, when we are training the VGG16 on the internet night for the federal learning framework, we basically transfer the 900 terabyte. That's a big number. And more importantly, people start to deal with the statistical heterogeneities in this federal learning because for all the devices, they actually have a very different hardware configurations, and also they handle different data. One important thing we learn is a non-ID, right? So non-identically distributed data, which means we actually data we share the different distribution, how we're going to handle these things. And if we consider the ID, the identically distributed, the data, the aggregate could be very, very high. And so here, 89% something for the Fed average. But for non-ID, they quickly drop to the less than 50%. And finally, we have the model inverse attack we'll show later on. It's actually when we're transferring the gradients of the model, so we actually already leaked the information because there are tons of adversarial attack based on the gradients we can transfer, and we actually can reverse engineering the original properties of the data and allow people to guess what's going on in the field. Okay, so we basically summarize the following 4 papers in my talk. The first one will be the LotteryFL learning, which was published last year, ISEC. The symposium on edge computing. The second one, the FedMask, is basically the updated version of this lottery network, probably on the census in 2021. And talk about the privacy enhancing and robust federated learning. The one paper in the CVPR talk about the defense against the privacy leakage on the federated learning for the representation perspective. Another one is Europe's last year talk about the poison attack. Let's talk about the lottery federated learning, which was probably last year symposium on edge computing. By the way, I'm the TBC chair of ESEC this year. So if you have any papers, I will encourage you to submit to ISEC. Okay, so we need a lot of the submissions. And the idea is very simple actually. So instead we're actually trying to train the models on each device by personalizing these models. The lottery federated learning use something called the lottery ticket hypothesis, to generate something we call the lottery ticket networks. What is a lottery ticket network? Lottery ticket network is basically you have a very generic network, and you have the subset of this network, which is a lottery ticket network, to represent the personalized property of the device. And every time you only deploy the different subset of this neural network, and so here different color coded to the different models to represent the machine learning model you need to have in these devices. Why does it become important? Because it's going to handle the non-ID setup, because we have a different data distribution, which will be represented as a different lottery ticket network here. And also the personalization, because of the different data properties that will be represented as the different subset of the network. We call the lottery ticket. And also because we don't need to transfer the whole bunch of parameters belonging to the whole, the graph or the neural network, we basically improve the communication efficiency by transferring the less number of the parameters, as we show here. So even sounds very beautiful, but the issue is how we are able to train the neural network like this, and also identify the lottery ticket network and to represent the different devices. So here's one example. We need to create a local lottery ticket network learning process to download the subset, from the server, and we need to identify this one. And we can prune and resize the subset, if the accuracy is larger than some threshold, we can say, oh, if the accuracy is a 75-hour requirement, we can further prune the neural network so that we can reduce the size of this lottery ticket network and still be able to satisfy the requirement of the accuracy. And we can perform the training on this local data, and update all the parameters belonging to this local lottery ticket networks. And this is basically how we do the personalization of the local training on this network. But the issue is, if we have this different lottery ticket network for the different devices, right, we need to send them back to the server, how we can do the aggregation, because there also something shares the similarity between different devices. So we need to handle this similarity. Otherwise, that's not going to be the federated learning rather than the individual learning. So we need to create a personalization preserving aggregation to handle both, the personalization we already done in the local, and also, the global similarity across the different devices. So the intuition here is we consider the non-ID data distribution across all the clients, and then the lottery ticket network of each client should not be significant overlap, each other. And based on this assumption, we can perform the aggregation on the only overlapped element among each lottery ticket network, while keep the rest of non-overlapped elements unchanged, because this unchanged parameter will represent the local personalization of the device. By the way, we're not the people propose this lottery ticket network. We just use this concept to do this federated learning work. So we try to evaluate, the whole process using the realistic non-ID setting. We only have limited, training data because it's linked to the reality. Each device has limited samples, so that we still need to have the federated learning. There are some papers show they have a large number of the training data on the device. then the question becomes, even if you have good performance, why you need a federated learning? So that's an unrealistic side. We have the heterogeneity here, only 2 classes of some samples on each device, because that's also represent the real case, right? If you have all the data with sufficient training data, why we need a federated learning? And we have a data unbalanced, which means that the one class of the data has significant, the larger number of the data than another side of another class. That's usually the case. So we have the baselines down along the Fed average and also the LG Fed average. Then we have global model with the local fine tuning. We try to evaluate the inference accuracy and also the communication cost. Those are the 2 metrics that we care about. We're trying to balance both. So the result basically show here. So when we are training, the CVPR over the 2,000 communication rounds on 20 clients, and the accuracy increase, by 13 to 15% compared with LG federated learning. It's a cross line can show here. And not even talk about the standalone or the Fed average. By the way, people are going to ask me, why standalone have a low accuracy? Because standalone basically means, we don't personalize, our model. Okay, we have a uniform model across all the clients. So, and the communication cost reduced also by 1/3 to more than 50% compared with LG federated learning, and we show here. So the interesting part is, if we're increasing the number of the samples per class, that we show in the local class, we actually going to reduce the communication cost, because we're either going to take the smaller number of the iteration to convert the model, or when we do the local prune training on the model, we can quickly convert this model to the much sparse the model we use. So both of the process actually reduce the number of the parameters we actually transfer between the local device and also the server. So that's the first thing we learned from this result. And also we want to train this one on unbalanced data, which means we have we call the balance rate. What is the balance rate? Basically, the number of the one class of the data versus another class. If you have balanced one, we have one by one. Otherwise, 0.5, which means 1 by 2, and 0.25 is 1 by 4. So we have very unbalanced data, and you can find out that it's a lottery ticket, well preserved, the personalization on the device, showing the better result on even very unbalanced data, as we show in the last column. And again, you start to see the reduction of the communication cost there too. So this the first topic I want to talk about. And then we have another paper about the FedMask. It's actually very similar for this idea, but we want to do one more thing, which is what we try to further reduce the communication costs associated with the training and also the computation here. So the idea is that rather than we have the lottery ticket, we basically the subset of this the neural network, we actually have carefully initialize the model with all the words, and then we have the mask. It's a binary mask, just 0 and 1, to filter out the part of these parameters from the local device to the server. So this you consider is a more like an upgraded the lottery ticket, so that the OR between the mask and also the original model will be considered as the new lottery tickets. But we don't try and transfer the lottery ticket, we transfer only the mask. And the mask is a binary. So basically we only transfer 0 and 1 between the nodes and also the server. So that is the trick. We actually continue to reduce the communication cost and also computational cost. And we try to learn the heterogeneous and the structural sparse and binary mask that we have done in the lottery ticket ideas. And we only communicate the binary mask between the clients and also the servers. And the binary mask will be element-wise applied to the frozen parameters to generate the personalized and structural sparse models, which can serve the exact same the task as a lottery ticket, does. Now, the question becomes again, how we are able to preserve the local, about the personalization when we're doing the aggregation. So that is the real trick we play here. So the idea is if we have this mask, okay, if all the masks have been prone for one channel, we don't really do anything. We just preserve the original mask, which are non-zero, and pass this one to the client. So if both copy for the different devices corresponding to the same channel are existing there, like the yellow and the blue, then we actually do the OR on this binary result and generate the green one here. For example, you have this both of one, you keep one. So one of this result is zero, you just do zero. So you're able to regenerate this aggregated mask and use that one to to deploy to the client. So this also be very simple. You don't really need to have any calculation, just a simple logical operation to generate the mask, right? And by doing so, you'll still be able to preserve the personalization, but you also do the aggregation. So result is like this. You have a frozen local model that have a lot of parameters, but you remember only part of these parameters will be useful to every single client, and the useful parameter will be filtered out by this heterogeneous binary mask trained by this process. And then if you do this add them on, you got the personalized model and deploy this model to the different devices. So we train so we train this whole design using the real system, which here we have the NVIDIA JSON TS2 or Nano or some Raspberry Pi, and then we have some switch connect all of this, and they show the different parameters, and also the different performance, so on and first, and even from different data, and the result basically show here's the result. You have a right start, that's the FedMask. So this basically shows trade-off between the accuracy and also the communication cost. So you will find out for the EMNIS of the CVPR or so on first. Our results give us the highest accuracy, inference accuracy with the lowest communication cost, and we show here. And black triangle is just along. It's actually show very low communication cost, actually zero, but it shows also the lower accuracy because they don't really personalize, the model. Another interesting one is it's being federal learning, the basically binary neural network. Binary neural network also have all 0 and 1. Okay? You don't need to have the floating point, the calculation, and so on first. What you have done is just a transfer 0 and 1. And it show very low communication cost, but also show the low accuracy here. So, and also some other baseline, I'm not go through all the details. So the binary things dramatically reduce the computational cost, because if you consider how we calculate this computational cost, we don't have any multiplication or division or some first. We're basically just a logical operation. This shows the inference speed up and energy saving tested from the real experiment. You will find out to compare with this our baseline Fed average with FedMask, and also the binary. You can find out actually with a good we have showed a good combination between accuracy and also communication cost, and we have relatively good, the memory usage compared with the baseline model. It's a small model than the original one. That basically means even consider we have the mask, but actually we have a more compact, the regional neural network, and all the computational cost will be the storage cost will be the 700 megabytes something compared with the baseline. The binary still be the optimal one because binary, the neural network itself is basically the binary. We cannot compare with them. But again, the accuracy is basically too low to be considered. Okay, so now let's move to the privacy enhancing and the robust federated learning part. So the first thing I want to show is the privacy leakage in the federated learning from the representation perspective. So how when we are transferring the gradients, there's a gradient will leak the information. How that can be the privacy leakage concept. Called the SAW theory, so published last year in CVPR. So motivation is this: the privacy preserving was already originally the major motivation for the federated learning. But recent work also show that the sharing the model updates or gradient actually make the model not just federated learning, basically make the machine learning model vulnerable to the property inference attack and the model inversion attack. And existing defensive approach, like a defense to privacy or some first, either generate significant computational overhead or negligible accuracy loss. So we try to propose a defense approach against this model inversion attack in the federated learning side. Well, by observing this data representation leakage from the gradients. And our contribution here is we try to explicitly review the essential cores of the leaking private information from the communicated local updates in federated learning from this data representation and develop an effective defense against the model inversion attack by perturbing the data representation. Basically, the trick is very simple. We're still going to perturb the input. That's the very simple idea. So let's talk about the data representation leakage in the federated learning. Those are some examples shown here. So when we talk about the federated learning, usually the data representation are less entangled because we have a less number of the samples on each device. And also in the practical federated learning application, the number of the batches and the local training epoch is also small. And it's a small, the number of the batches and local training epoch induce a number representation and entanglement, entanglement for other. So based on this analysis, if we have the algorithm that can basically extract the class-wise feature from each device uploaded, updates, could be very efficiently show the leakage of the information. So the left column is the ground truth, and the middle column is the WG, which stands for the whole model gradients, which is exposed to the server. And the CRG is basically the convolution layer only for the gradients. And also the representation is basically the inference data representation using our methods. So you will find out that if we just expose the gradients from the convolutional layer, it doesn't really give us much information. Okay, there's still be the mass because this feature is not be able to use to represent the original input. But for any others, you can clearly see we are able to do reverse engineering from the original data. This by the way, the more data in one batch you include, the less opportunity you will be able to do something like this, okay? Because all the features will be entangled together. So we are able to train a model to do this data representation attack. This is one I'm going to show here. We have we have the model. The model can be trained, to basically, restore or reconstruct, the original information. So our goal becomes, number one, how we can reduce the privacy information leakage, or say the reconstructed input, applying through this perturbed data representation, and the raw input actually be dissimilar, because we want to make sure there's no way for us to restore this information. And the goal two, to maintain the federated learning performance, because it still be the key parameters we're going to retain. and the perturbed data representation are prime, and the true data representation are without a perturbation should be similar, because we don't want to apply the larger noise to do this, or that becomes the metric for us to do the perturbation. So you can imagine that we try to minimize one thing and maximize another thing. That's basically something we're trying to do. So we can formulate, the defense of different method as I show here. Here, F is the representation structure in the model, and we have basically trying to apply, the dissimilarity while maintain the similarity as the input. That's something we have done. So that we have different choices on how we can measure the dissimilarity and the similarity, because this also give us the different implication. For example, when with L1 node, that basically shows the similarity between the two vectors, that will directly represent the data we're going to transfer between the server and also the client. But if with L2 node, that become the RMSE. That'd be very common metric, so we can measure the image, the quality degradation. You can also use some other metrics, like the ISSM on the first. It's just one example. But the reason we use this Q equal to 0 and also the P equal to 2 is because we can derive, the analytical bound, for the certified robust and the guarantee that we show here. It's basically talk about the dissimilarity as reconstructed, the figure, and also what the figure will be larger than some bound. That will be the lower bound we can guarantee here. That's what gave us very beautiful, radical guarantee here. I'm not going through detail. You can read our paper for this. So we try to evaluate, the whole things on the non-ID CVPR 10 and the non-ID NIST. So we have two attack method, one with the deep leakage, from the gradient DRG attack, and also the gradient similarity attack, the GS attack. And what we're trying to do is we're trying to make sure we have, even have very large RMSE at the input, which is so the dissimilarity for the perturbed data and also the original data will still be able to maintain very high, the model accuracy. So the defense, baseline will be the gradient compression and the differential privacy. And you can find out that, for the defense baseline, if we change the MSE a little bit, then the model accuracy will drop significantly. That basically means that it won't work. Even if we cannot have the good trade-off between we maintain the accuracy of our federal learning model with the perturbation of our input result, to basically prevent people from reconstructing the original data. But the black line is our result. You can see that even increase the MSE significantly, which even this portion can be visually perceived, then we still see very minimal accuracy loss for the original federal learning model. So that is what we want. And actually, even for the RMSE becomes 0.8, we'll still be able to see almost the same accuracy compared with the original one. Okay, so the last topic I'll talk about today, it will be the enhancing the robustness against the model poisoning attack. The poisoning attack is not new, right? People have been using this poisoning attack to attack the machine learning model for many years. And also use a different way to generate this poisoning attack samples, like the generative adversarial network or something first. So what we found out here is the model poisoning attack is going to fool the global model to produce adversarial misamplification on specific and malicious data set with high confidence. That's something we actually know. It's not new. But the only difference is, for the federal learning setup, even for one poison attack from one client will generate a long-lasting effect here. And the current server-based defense cannot guarantee the robustness when the attack is extremely large. If the attack is so small, yes, we have so many clients, we maybe amortize the whole attack. But if we have like the 50% of the clients are malicious, there's no way for us to do this work. So when the server-based defense fails to defend the poison attack, then the attack effect will remain in the global model for a subsequent round, even without attack occurring. We're going to show you why that is the case, and also to show how we can prevent this from happening. So our work is trying to review why the model poison attack effect can persist in the global model for the consequent rounds, and also to propose a defense to mitigate the long-lasting model poison attack from a client perspective. And we can review the reason for this long-lasting effect and develop a defense against this poison attack from a client perspective by, again, perturbing the part of the local training gradients, not the original samples, where the attack effect is residency. Let's look at this. So to investigate the robustness of our current method under the challenging but practical attack setting, we evaluate several popular server-based aggregation to show the result, including the CMA here, and also that is a coordinate median aggregation. So a black circle basically shows the run that is adversarial run. That basically means there are some attack show up and conduct the model poison attack. So in each communication round, the 10 devices are involved in the training. So the NM here means how many clients are participating in the attack. If the NM equal to 1, basically that's fine. People can, and this federal learning can easily bypass this attack. But when half of these devices are participating in the attack, they start to accuracy drop significantly. And even you don't have this attack in the middle, you start to see the accuracy drops will actually last for a while until they can be amortized again by the training. So how are we going to handle this? So we actually create the attack effect on the parameter. That's basically some parameter to quantitatively measure the impact of this poison attack that's here. And we found out the long-lasting attack effect residence in the kernel or the num space of the Hansen matrix during the local training. And we start to this derivative actually going to last us for a while, and this get close to 0. The parameter will actually become the vulnerable element to be affected. Okay, so based on this, we actually propose we call it FLWBC, or white block cell for the federal learning, a client-based defense. So each client will act as a white blood cell, in the federal learning system. So which mitigates the poison attack effect that is not defended by the server during the aggregation. So goal 1 is trying to maintain the benign task performance, because that is our original goal. The loss of local benign task should be minimized, while we try to prevent the AEP, that is the parameter we define for this long-lasting effect of the poison attack, from being hidden in the kernel of the Hansen matrices on the benign devices. So the kernel of the Hansen matrix should be perturbed so that we don't have this sensitive region, and we show here. And what in the reality, we actually don't really calculate the Hansen matrix. We actually handle the derivative between the current round and the following round, so that we calculate the difference to simplify the computation. Okay, so the evaluation like this. We actually invited our method on the fashion MNIST and OC CVPR10, but we did not show the CVPR10 result here for the simplicity. And we have 10 clients participating in the training for each round, and we have up to 5 malicious attacker in the adversarial round. We have a different defense baseline, including the coordinates, median aggregation, coordinate the trimmed mean aggregation, the local differential privacy, and the global and central differential privacy. Basically, we try to either perturb, this input, or they try to, during the aggregation, they try to minimize the impact on some malicious, result. So the result basically show is very simple. For the baseline, they're not be able to handle the attack very well. In many cases, they can last 5 or 10 rounds, then they drop the accuracy significantly. But for our result, it's IFL-WBC, and even for the noise, it can be very, very big. We still be able to achieve very good defense here. Another thing is talk about the impact on the standard deviation of the noises, because the larger noise basically means the stronger. Basically means the stronger defense. So what I'm going to show here is if we are able to have the attack, we are able to increase this. We're able to increase this noises and also some parameters with the IFL-WBC only inject the propagation to the parameter space while the long-lasting AEB, but instead of the perturbing all the parameters like the differential privacy, let's end up with a much better trade-off curve as we show here. So basically, we have for the same, the mitigation round, means how many rounds we are able to last. We can have a much better benign accuracy, and we show here. So there's a Pareto front here. That is right star. It shows much better results for the different for the different noises and size. And we show here. So. To recap, what we have done, we actually have a lottery ticket, network. That's basically we're trying to combine the personalization with, to reduce the communication cost, and then we try to further improve that one with the binary mask, because we know the binary is the minimal effort that we could do in terms of the personalization, and then we talk about privacy concern during data representation to restore the data. And talk about the poison attack. That will be the long-lasting effect, particular of interest to us, how we can solve this problem. So a little bit one more thing, because I'm directing this AI Institute at Duke, with this to capitalize and respond to the challenges by advancing AI technology used in the edge computing. We have 7 universities and lab by Duke, and also several industrial collaborators. And we are working on the networking, computer system, AI services. That's why you see why I'm interested in federated learning. It's not only for the theoretical part, but more from the deployment of the real system. So if you're interested in, you can access our webpage, find out those details. I think I will stop here and open for any question you may have. Yeah, thank you. Yeah, please.
Yeah, do you want to
or this one? I don't know.
Yeah, maybe here.
Oh, here. Okay, yeah, sure. Oh, the mic there. Okay.
Yeah.
Hi, Vice Chen. Thank you for the talk. I just wanted to ask you about the trade-off between communication efficiency, privacy, and the computation cost of the clients. And do you really think there's a trade-off between them? And in practical scenarios, which ones are the most important? For instance, could we have an algorithm that takes a lot of compute time for a client, but is super private and super efficient communication efficiency? Would that be a useful use case in practical scenarios? Thank you.
Okay. So this actually be very good question. So usually when we are designing a system, we have some goal, performance. For example, we talk about the machine learning. We say that the accuracy is a golden requirement. We need to achieve like 95% accuracy, and then we talk about something else like efficiency or something first. But federated learning is a little bit different because it's really hard to quantitatively measure the privacy, and you have tons of ways to measure the privacy, and no way for you to achieve 100% accurate privacy. So eventually we'll find out that become, everything will become the soft, requirement rather than the hard one. So which means we don't have such a golden standard, then we worry about something else. So you can find a good trade-off between how many percentage accuracy will drop, then you can improve the communication cost by such and such. So then that become very practical trade-off you're going to make. In reality, I will say the communication and the competition cost will be hard coded because it will rely on the network bandwidth and the computing hardware you adopt, and also relevant to the latency requirements on the first. That will be harder than the privacy. So I will say people always are trying to maximize the usage of this hardware, then worry about anything else, unless your boss tell you saying you have the higher budget to replace those stuff. Otherwise, this will be something it will be capped. So I think that's usually the real design philosophy we have here. Yeah, sure.